So we are in SER222, Applied Data Structures, Algorithms, something like that. We're using the course Java Structures by Lewis and Chase. You can be looking at the 4th or I believe the 3rd edition will work just as well. And we're looking today at the introduction to collections, and in particular we're looking at stacks. So we're going to talk a little bit about the concept of a collection, terminology that surrounds collections. There's a Java Collections API which has a whole bunch of classes. I think you brought some sort of a homework problem that asks you to try to list them all, which is really about you learning how to navigate the API document. And we're going to talk about sort of abstraction, which is a really important concept in object-oriented design and also in analysis of data structures. And we're going to look at a particular data structure, a very simple one for dealing with collections. It's actually kind of a restriction on what you can do with a collection. We're going to look at what a stack is conceptually, how you use it to solve problems, and we're going to look at one possible way to implement stacks, and later we'll look at another way. So first of all, the terminology around collections. When we say collection, it's just a generic term for anything which holds and organizes, manages other objects. So a bunch of them, though, right? And that's kind of really what the whole course is about to some extent. Generally, in a collection, you have operations that will allow you to access and manage the elements, perhaps add or remove, and peek at the elements, either at one end, like the beginning or the end, or maybe at arbitrary spots, or pull out the minimum one or the maximum one. So there's different methods, different questions that different types of collections can answer about the elements within them. Many standard collections have been defined over time, and when you've got a collection of data, there are different ways to organize it. One way, like the shipping containers, right, is put them all in a line, and that's probably the most common that you've seen before with arrays. But it can get really complicated as well when you're trying to model things that match real world. So if you're modeling genealogy, like a family tree, you might have collections which are nonlinear and look like a hierarchy or a tree. Your file structure in your operating system might look like a tree. The object, the class hierarchy looks like a tree. So certain things they're inherently trees. Sometimes we organize things as in trees because it makes it very efficient to search them for, like a binary search tree is a data structure that allows you to very quickly locate an item you're looking for in the collection, versus arranging them all as a flat list. So linear and nonlinear. This is nonlinear, but it's still organized fairly simply. Sometimes if you're trying to model the internet or networks, the organization can get very messy and chaotic. So another important idea here, which we're doing when we talk about collections already, is abstraction. So abstraction is really a process of hiding details that make a concept easier to manage. And we've been doing this the whole time we've been programming. You start just by looking at operations, and then you can hide the details of those particular operations behind functions. So instead of having to say add 3 to this, subtract 4, divide 2, you just have some method that does something. And then you just say call that method. So you're abstracting a little bit. And then you're abstracting your data into classes, right? And so you don't have to talk about exactly how the data is laid out. You just say it's a person. And so that abstraction kind of continues, right? So even more abstract. We're talking about the concept of a stack in general, and it could be a real-world stack of quarters or a stack of Pringles potato chips or whatnot, and we can talk about it and reason about it just the same way that we reason about the data structure that we're going to use on a computer. An important concept when you're talking about abstractions is we don't talk about how things are implemented so much as what operations they support, or rather the interface. So in object-oriented programming languages, there are often mechanisms that mirror the way that we think about algorithms. So by just providing an interface without implementations in Java is a kind of abstraction. One way to think about abstract data types is they kind of encapsulate the object's data and the implementation. So we can talk about a stack, but then we can implement that stack using arrays or linked lists, or different options exist. And object-oriented programming languages have great mechanisms to help us implement these, or to do this. An abstract data type. So a data type is really a group of values and the operations they support. And you're not going to think about how those, usually in an abstract data type, you don't think about how they're arranged in memory or anything like that. For instance, a number, right? So a number, a natural number, right? It's the set of values 1, 2, 3, 4 on up to infinity. You already can't represent that on the computer, right? But you know what they are, and they support operation. And you can describe the operation in terms of things that must be true, like about them. So addition and subtraction, you can multiply, you can compare them. So there's these operations that numbers support. It's an abstract data type. It's really a mathematical thing. Whereas then a data structure is the set of programming constructs used to implement them. So, when you're talking about it in software, you might say, well, an integer, you could represent it in 2's complement, you could represent it in sign magnitude, you could represent it in unary notation, in hexadecimal, you could have it represented as a decimal string, which has some big advantages. You could have a big int in Python or something. So there's different ways that you can arrange these bits in order to represent integers. Most of you are probably most familiar with 2's complement being used to represent integers, but that's not the only way. There's different ways to structure. So the abstract data type has to do with the values and the operations. The data structure would be more how you're laying it out in detail. It's more detail, right? The distinction between the two is often blurred in casual use. It's a gray line between data structure and abstract data type. So. And then there's the concept of an interface. And an interface is the programming language construct in object-oriented languages, which is most similar to an abstract data type. It really, all you see are the knobs. You're completely hidden from the details of how it's implemented. And you can think and you can reason. Over here, you can be writing your code completely using an interface, and some other team of developers can be providing multiple ways to implement that interface so you can pick the best one. So it's decoupling, it's abstracting. So dealing with collections of data is a big part of why people use computers. And so there's a lot of support for that in the Java API. Java has sort of this collections framework, this subset of the Java stuff that comes with Java that just deals with collections. And I think that they mostly live in java.util.something. And you're going to have a whole bunch of them. The one that people use the most nowadays is array list. It used to be vector, which is another kind of array list. And then, but you have linked lists, and you have hash tables and hash maps and sets and stacks and queues and binary search trees and heaps and there's just a whole bunch of them. The double-ended queues or decks and so there's a whole bunch of them that you could explore in that API. So poke around, see if you can find a tutorial a tour of them, and why would you choose one versus another? That could give you some good insight. But Java has a whole bunch of them. I think they have a master just a generic collection interface, and then a lot of implementations, and then the implementations will be more or less efficient for different operations. So as we explore any particular collection, we're also going to examine any support provided in the collections API for that collection. So when we talk about stacks, there's actually a stack class already there for you in Java. And unless specifically directed otherwise, when a problem asks you to use a stack, you should use the Java stack and not make more work for yourself by implementing your own. You know, that's a part of being a good developer is knowing when to reuse, right? What to reuse. So what is a stack? It's exactly what it sounds like. It's a classical collection. It is used in a lot of problems. it's really limiting what you can do with a set of objects to mimic what would happen if you had like a can of Pringles potato chips, right? When you reach into the can, you can't pull the potato chip out of the bottom. All you can reach is the potato chip at the top. And if you were going to put a potato chip in there, the only place you could put it is in the top. So you can only pop from the top, and you can only push to the top. It's the last chip that you put in would be the first chip that you take out. That's how stacking works. And so they call these things LIFO, last in, first out. Wonderful acronym. You can think of a stack of books. You add to the top and you remove to the top, but if you try to pull a book out of the middle, it's likely to fall apart on you. So this is sort of the illustration of a stack. You can see what's at the top of the stack. If you add an element, it goes to the top, and if you remove an element, it comes from the top of the stack. Very often these stacks are drawn sometimes upside down. So stack operations, push is, I guess Pringles, right? But you push in and you pop out. Once you pop, you can't stop, right? So you keep moving them from the top of the stack and you push them into the top of the stack. Peeking to look and see what's in the top you could do. And then since it's a collection of a bunch of items, it's useful to know whether you run out of items. Is it empty? And then also how many items do I have? Right, now we understand, hopefully we understand, at least abstractly, what a stack is. Now we can begin to talk about what it would take to implement stacks properly in Java. And we can talk about the way that they are implemented in Java, which is probably not the right way that they should have done it. They did this a long time ago in Java, and after they did stacks, they kind of realized they did it wrong, I think, and in the future they kind of organized their data structures a little differently. But there's some important object-oriented concepts that we're going to think about before we try to design our own stack data types. So several of them, we need to rely on compatibilities, interfaces, inheritance, and polymorphisms. So morphisms, yeah, right. Review those concepts is necessary. Slide tells you to do that. I agree. And then there's also something that was introduced into Java called generics, and it was great when they introduced it, and we're going to use generics when we implement abstract data types. And generics allow us to not have when we make a collection, usually you want to have a collection of something, a collection of books, a stack of potato chips. It used to be in Java, if you were going to make a collection of stuff, it was pretty much just a collection of objects. And I could put a potato chip on top of a book on top of another potato chip. And sometimes you want to say, no, that's terrible. You'll crush it. You want to be able to say, this collection can only hold books, or it can only hold potato chips. And generics are a mechanism that allow us to enforce that restriction in Java. So suppose we were to define a stack of object references. In Java, that would do what I said. It could hold anything. You could hold anything in the collection. That doesn't mean that any item in that collection could be different. You could have an integer, and then you could have a double, and then you could have a string, and then you could have another integer, all in the same collection. You lose control as the designer of that data type over which types of elements are added, and not only that, since the compiler doesn't know what's in the stack, whenever you try to peek or remove something from the stack, it's going to provide it to you not as a book or a double or an integer or whatever it is. It's going to give you an object, and if you want to see it as a book or an integer, you're going to have to do a typecast. So if you had a collection of objects, every time you peeked or removed from it, you'd always have to typecast the thing that you got in order to see what it was back into what you think it is. And then you have to do error checking and all of that other stuff because you don't know if somebody's messed up. So without the ability to constrain what goes into the collection, you need to do a lot more testing and a lot more code to do typecasting. So a better solution is to have some way to restrict the collection to a particular type, and that's what generics do. The type when you're creating a class stack, you can say that I'm creating a stack of T, and T is really some placeholder type that when you actually create the stack, you plug it in. So I say I'm a stack of integer, or a stack of double, or a stack of book if you have some class book. And so what does that look like? When you're defining the class, at the end of the class's name, you can put in angle braces T. And you read that class box of T, of, for those angle braces, right? And T for type or E for element are pretty standard names. And then when you go to instantiate that class, right? Out here, you're going to create a new box. You have to plug in an actual class in there to fill in that placeholder. And now you've actually got a class, box of widget, right? So a box of widget. And on the left-hand side, you have to assign it to something compatible. And now this box 1 class, its type is box of widget. All you can insert to it is widgets. And when you pop or peek, what you see is not an object, but it's a widget, and it has all of the methods and properties of a widget accessible to you without you having to typecast. If you try to do anything, insert anything else in there, you get an error at compile time. So that's nice, a little bit less testing for you. There we go. So, you can actually use that same generic class and substitute something else for T. So you can make a box of gadget. Right? Now box 2 is a box of gadget. It can only hold gadget objects. And unless a widget is a type of gadget, it can't hold any widgets. So you can kind of keep those things separate. So generics are a tool that allow us to constrain what goes into a collection. At runtime, they're always just collections of object anyway. But this is sort of, it makes it easy for people to use the class because they can ensure that it always has the same thing, and then they don't have to do any typecasting to see it. So let's look at, so that's kind of how you design the interface to have a box of a particular type. Now let's look at an example that uses stacks, and then we'll see some code that uses stacks to implement these things. So postfix expressions are a convenient way to represent math. When I was studying math, we used to use Hewlett-Packard calculators that used this notation for math all the time. It's called reverse Polish notation, is what they call it. But it's really postfix expressions. Postfix means that the operator follows the operand. So instead of 15 minus 8, you say 15 8 minus. Right? It's equivalent to this, which is infix. There's also a prefix, which would be minus 15 8. So there's different ways to represent it. The beauty of postfix expressions is you don't need any parentheses. So it's very convenient if you have to write code that interprets any mathematical expression. That you can, if you can ask your user to somehow put it into postfix, hopefully they've used Hewlett-Packard calculators and it's easy for them, then you don't have to deal with this sort of nested parentheses and making sure you evaluate the inner part first and then move out. And order of operations where you do multiplications first. You don't have to worry about any of that stuff. The postfix expressions just work perfectly, and all you need to evaluate a postfix expression is a stack. So how do you evaluate them? You're going to use a stack as follows. You're going to scan that expression from left to right, and for each operand, like a number, you're going to push that thing onto the stack. And whenever you hit an operator, you're going to pop off first the right operand and then the left operand, and then you're going to apply that operator to those, and you're going to push the result back onto the stack. When the expression is exhausted, so after you finish that string, the stack should only have one value on it, which is the final result of the expression. So if anything else happens, the expression was ill-formed. So here's how the stack changes in this expression. So what are we going to do? We're going to push 7 onto a stack, then we push 4 onto the stack, and we push negative 3 onto the stack. Then we hit the multiplication operator. So we're going to pop negative 3 as the right operand, 4 as the left, and we're going to say 4 times negative 3, so we get negative 12, which we push on top of the stack, so that those get replaced by this. So we have 7 and negative 12. Then we hit a 1, which goes on top, and a 5, which goes on top, Then we hit a plus. So we're going to do 1 plus 5 and get 6, which goes on top of the stack. Then we have a division operator. So it's important that you think about what's left and right here. First we pop off the right operand, then we pop off the left, and we're going to do 12 divided by negative 12 divided by 6, and we get negative 2, which we push back onto the stack. And then we hit a multiplication operator. We're going to do we're going to do 7 times negative 2, which gives us a 14, which we would push on top of the stack. When we're done, that's the only operation on the stack, and that's going to be the correct result. So how would you actually write this class? So first off, whenever you're writing code, let's talk about a couple of things. One is you're generally going to write some sort of a driving application, and you're going to have another class file which actually has your class that does the interesting work. And the driving application is really just there to help you test and exercise the code to make sure you got it right or to demonstrate that it's correct to me. In this case, we're going to call this thing a postfix tester. Its main purpose is to test the code. And what it's going to do is it's going to ask the user to enter an expression, then it's going to evaluate the expression, and it's going to keep doing that until the person says that they don't want to do it anymore, right? So we can look at this is the driver application that uses a class called postfix evaluator, which is actually the class that does the work, and that'll come later. So the first thing to note is we're using java.util.scanner. If you haven't used scanner before, we're going to use scanner whenever we want to bring input in from the user, because it allows us to parse, to tokenize what the person types, and to split it and to get the next integer or the next double or the next float. Get the tokens and turn them into the proper type of thing. So we've got a class postfix tester. These are javadocs with the double stars. If you do not know what javadoc is a formatted comment used to describe the class. It uses things like @ to indicate these special fields. And there's a tool you can run over your class which generates an API reference manual as HTML by parsing the javadoc. So you want to learn about javadoc, how to use it, and how to describe classes in it. So we have a postfix tester. Reads and evaluates multiple postfix expressions. This is the main, public static main entry point. So what we're going to do is we have a string for the expression and a string that indicates whether the user wants to do it again. And then we have an integer, which is going to be the result of our postfix expression. A scanner is going to read input from system.in that the user types, and it's going to translate that for us into tokens so we can pull them in one word or number at a time, or line of text at a time, depending on which methods we call from scanner. Now we have a do-while loop. So it's going to do this once, and then it's going to check whether it should do it again. It's a bottom testing loop, and in the do-while loop we create a new postfix evaluator. That's a class which we're going to define later. And then we ask the user to enter a valid postfix expression, and we give them an example. Then we say each token must be an integer or an operator, and we list the operators. So that's just nice of us to tell them what valid input is. We use the scanner in to read the entire line of text written by the user. And then we use our evaluator to evaluate that string, that postfix expression, to get our result, which is an integer. We print a blank line, we say that expression equals, and whatever the result is, we ask if it should repeat. We get the next line, and if that next line, we skip so we don't stay on that line. If that next line is an upper or lowercase y, then the loop repeats, otherwise we break out the loop. So that was pretty basic, but it's good to go over the driver code at least once. Now we have the postfix evaluator class, which actually does the interesting work of understanding that expression. And the reason that we separate out from the driver is this thing is reusable, right? So how does this work? In java.util, there's a stat class. Again, we don't have to implement our own, although we will. This exists already, and we can use it. And of course, we're going to use a scanner in order to split that expression string into tokens. We aren't going to be interacting with the user in this class, though. Good style is to use constants at the top in all uppercase, rather than to have strings littered throughout your program. So we might want to use different constants at some point in time for some of these. And our postfix evaluator, what it's going to do is, remember when we evaluated the expression, we're using a stack, and so this postfix evaluator is going to have a stack as a instance variable that's private. It possibly could have been inside of the evaluate function, but we're going to have it as an instance variable. The constructor, the default constructor, just default constructs the stack. So this will be an empty stack of integer. So here's the important routine, the one that evaluates an expression. Again, it's commented in JavaDoc. When you're doing JavaDoc, you document the parameters with @param, the name of the parameter, and then a human readable explanation of it. Right? You do the same thing with the return value, @return, and then explain what you return. So for this guy, for the evaluator, remember when we evaluated these expressions, we'd pull out a left operand, a right operand, and we would then calculate a result which we pushed back onto the stack. This big long expression can be split into tokens, and those tokens can be classified as operators or operands. So we're going to use a scanner for the tokenization. So we're going to create a new scanner that can read from this string and tokenize it. While our parser has a next token, so tokens are separated by white space here. We're gonna get that next token, and we're going to check to see if it's an operator. So this is a function which is going to be defined later in this class, but this just checks to see if it's plus, minus, slash, or times. So if it is an operator, we're going to pop off the right operand. So notice we get the second operand and the first operand kind of in reverse order, right? And that operand is going to be of type capital I integer, because our stack, if we go up here, is class integer. It's not an int, it's a capital I integer. Generic types, that T that goes in there, has to be a class type. You can't use built-ins. So you can't ever have a stack of int. You can only have a stack of cap I integer. And when we want that lowercase I int value from it, we have to use the int value method of class integer. So we're popping from the stack, and we're taking that result and getting its int value. Again, here we're popping from the stack and getting the int value for op1. Now once we have those two operands, we can, again, in order to keep this code simple, we have another expression, another function that does a single operator. So we pass in which operator it is and the two operands. Then we get a result which we push back onto the stack, first casting it back to an integer. So you'll see that this does some extra code that your version of Java may not require. Like, you probably don't need to call .int value, and you probably don't need to cast this to an integer. Older versions of Java might have required this, but your version of Java probably does auto boxing, and so you can just use stack.pop and push result. However, if the thing that you get isn't an operator, then that means it must be an operand, and what we do with operands is we take this token, which is a string, and we use the parseInt function from integer, which returns a lowercase I int, and then we'll box that, we'll turn it into an integer and push it onto the stack. And then, so hopefully after this loop is exhausted, there's only the result of the last expression evaluated is the single item that's on the stack, and that's also what we need to return. So that code used some helper functions. One just checked to see whether a token was an operator, and it just does a brute force search. You'll notice that even though they defined constants in the class, they didn't use them, and all I can say is the author's code is imperfect, right? So you probably should have been using the named add, subtract, multiply, and divide, rather than dropping those string literals in here. The other thing that we had was the evaluate single operator method, and that's very simple. It's just using a switch statement, depending on what the operation is, and here they actually use the names. It's going to either do plus, minus, times, or divide with op1 and op2, and return the result as appropriate. And that's it. So you've got an entire postfix expression evaluator as long as those expressions are entered in postfix. I don't really expect you to ever use that class, but it's good to know how to do that. Right? So the postfix, just as a warning, you might encounter a problem in your homework that says do something for an arbitrary mathematical expression. That problem isn't asking you to implement a postfix evaluator. That problem is asking you to do something for any mathematical function. So you can just type it into, hard code that mathematical function into your program if you want. When you hit that problem, ask about it if you're not sure on the discussion board. But you do know, if you ever had to, now how to evaluate arbitrary mathematical expressions as strings if they're entered in postfix. It used java.util.stack, and that's been there since Java 1.0. It violates the current best practices for design, and I'll explain what that means. Stack is not an interface, which it should be. There should be an interface stack and then an implementation called array stack, because that's what we were using. The stack that we were using is implemented using arrays, right, or dynamic arrays that can grow and shrink. But that's not the only way to implement a stack. Okay? There's not a lot of consistency, as the slide says. They acknowledge that there's not a lot of consistency, and that's just because of path dependency. Java was old, and then they figured out eventually how they wanted to do things. What does this function look like in UML? Again, we always want to, in object-oriented, we want to go back and look at the UML and make sure we understand the UML diagram as well as the code. We've got java.util.stack, and this little dotted line means that there's a generic parameter t. We should recognize this as the implements arrow, right? So this means that this is a specialization of that, and like this is the interface that implements. This indeed is actually a special kind of arrow. It's binding t to integer. So it's turning a generic class through specialization into an actual class. Right? This postfix evaluator is our driver code. Not our driver code. This postfix evaluator is our new class. This does something useful. And it uses a stack. And then this is our driver code. This is our driver code that uses our postfix evaluator. So you saw a lot of JavaDoc comments that began with the slash and the 2 asterisks. That's called JavaDoc. There's a tool, and from your let's try this. So I've got here IntelliJ, which is what I use for Java, and if you're using a Eclipse or something else, your tool probably has support for JavaDoc. And if you put something in there like this is JavaDoc, I don't know, and you can put tags in like @ and then AU, and in control space on this tool, and usually that'll help you autocomplete things even in the comments. There's certain fields which are understood in the JavaDoc. So this is written by Femiani, and then there's different fields that you can use. If it's deprecated, that means that this class shouldn't be used anymore. C, you can refer to other classes. Sint, and you can say it's Sint, version 1, right? Whatever. You usually have some sort of tools to generate the JavaDoc as HTML that you can then inspect. So let's see what we've got. Yeah, generate JavaDoc. I'll do it for the whole project. And then open it in the browser. What does it need? It needs to know where to put it. So it's going to generate a whole bunch of HTML files, and I'll just call this temp docs, right? Because I'll delete it later. I guess I have to create it. Temp docs. Now I can press OK. It's going to go through. It generates a Java HTML documentation. Looks all professional and stuff. And it should pop it up in a browser window. Let's see. It's over here. So there's my class main, and it has a static void main function. And if I look at that main function, oh, yes. Remember my JavaDoc, I said this is JavaDoc, and it was since version 1. So it's generated this JavaDoc API reference manual. It looks just like all of the Java API docs. So if you comment your code properly, you can generate these wonderful manuals that look all professional and slick. And it's just good habit so that your code can fit into other libraries, and then they can generate this huge manual from it as well. So we try to use JavaDoc. The API documentation for Java itself was generated using JavaDoc. We got that they begin with // they begin with the @ symbol, and in IntelliJ at least, if you do control space, it'll show you some of the things that you can put in, some of the tags. We got that. So exceptions, again, I think you should have probably seen exceptions in 200. At least you know hopefully how they work, but now you're building your own classes that are data structures that are using exceptions, and you got to answer when should an exception be thrown from a class. And all of these decisions people can argue about, right? Generally, exceptions should happen for things where, how do you say? If we can handle it, we shouldn't throw an exception. So, exceptions are part of the interface. So an exception shouldn't be thrown for an implementation detail. An exception should be thrown for a violation of the semantics of the data type itself. So, for instance, running out of space in your array shouldn't generate an exception, but trying to pop from an empty stack maybe should. So there's no concept of full in stacks. So you shouldn't throw exceptions for full, because that would be an implementation detail, right? But there is the concept of a stack being empty, and then you try to pop from an empty stack. That's clearly wrong. So yeah, you should throw an exception, because that becomes part of the interface for your stack. So in Java, the API did not rely on a formal interface, but we're going to kind of do our own implementations of stack, and we're going to do it right. We're going to make an interface, and in order to distinguish it from Java, since Java already has interfaces for all these things, we're going to add the words ADT to the end of all of our interfaces in this course. So our stack interface is going to be called stack ADT, and we're also going to put it into a different package, which will further distinguish it. And we're going to call it Java Software Structures. Well, whatever. JSJF, right? We're going to call it JSJF. That's our package. So here we go. So in a folder called JSJF, we can define an interface called stack ADT. The interface is generic of type T. We're using JavaDoc for all these methods. We can push an element onto a stack. We can pop an element from the stack, and we get an element of type T. Right? We can peek at what's on the stack. We can check if the stack is empty. Notice that pop may throw an exception, but it's an unchecked exception, meaning that we don't have to declare that it throws exceptions here. even though we didn't put a throws line in there, so throws empties collection exception or whatever it's going to throw, we know that popping from an empty section a stack might throw an exception. The reason that it's not a checked exception is because the user could presumably check if it's empty first, so it really indicates misuse if that exception is thrown. If you don't know what a checked exception is, you should have learned that in 200. Maybe you forgot. Google it. Check. Okay, and you'll find the answer. Right. And the interface includes toString. It doesn't have to. I don't know why the author always puts toString in the interface, because every object already has a toString. So it really doesn't belong in the interface, but we'll live with it. So here's what that stack interface looks like. It's an interface, and we know because of this role here in the UML diagram. It's generic because of this little t floating up on the side, and it's generic with parameter t. And here's the interface. Here's all the public methods. They should have pluses in front of them, but there's all the public methods. Right. So now you've got this interface defined. There is more than one way to implement this. So later we're going to see how to implement stacks with linked lists. For now we're going to implement a stack with an array, very similar to the way that Java's built-in stack work. Right? Since we're using an array, in Java, an array is a certain size, and once you have that many items in your stack, you can't add any more. So the size of the array is kind of our capacity, and so we'll allocate an array of 10 elements, and they'll all be null, right? And then we're going to push something on, and we're going to push something on, and eventually we push 10 items into this array. We don't have room for any more. We're going to have to copy that into an array which is twice as big. And so we're going to have to deal with what happens when the array gets full. Okay. So an array in Java just stores references to the objects. I kind of alluded to that before. So initially the array would all be nulls, and when you push things on, the array element becomes a reference to the object. It's important that when we remove something from this array that we set that reference back to null. If we don't do that, that object referenced by the array will never be removed or deleted by the garbage collector, right? That's a memory leak. So whenever we're holding on to an object past when we need it or want it, that's an example of a memory leak, and we don't want to have those. Okay. So we're going to call the number of cells in an array its capacity, and that's going to be different than the size of the stack, because the capacity is how many elements you can push before you need to do extra work to resize it. It's not possible to change the capacity of an array in Java. Even though I said resize, you can't actually resize arrays. All you can do to expand the capacity is make a copy of the original array that's with twice as much room. Fortunately, there is a function in Java designed just for making that copy, and we'll see it happen. Another thing that's important is it happens infrequently. And if you wanted to do the math, you could figure it out. If I insert 10 items, and then when I try to insert the 11th item, I double the capacity to 20, right? And then I can insert 10 more items. Right? So that means the first 10 items were copied once, and the second 10 items weren't. Right? So it's after I insert the 21st item, I'll double the capacity again to 40. Right? And I'll end up with 20 items. I can put 20 more items in before I need to reallocate again. So each time I grow the array by doubling the capacity, I can insert more items before I need to resize. And if you do the math, half of the items, 1/2 of the items, were never copied. A quarter of the items were copied once. 1/8 of the items were copied twice. Right? So if you look at, if you kind of do the math on that, the number of copies is going to be 1/2 plus 1/4 plus 1/8 plus, and it's going to keep going like that. And if you ever took calculus, you know that this series, this is another series, right? Last lecture we talked about arithmetic series. This series, the sum, so 1 plus 1/2 plus 1/4 plus 1/8 plus, that whole thing sums up to 2. That's it, 2. Right? So the most, so if you add all that stuff together, on average, for each element in that array would have been copied twice. That's it. No matter how big the array gets. So that's kind of amortized analysis. If you do the bookkeeping, as long as you keep doubling the size of the array when you insert new items, it's really free. That even though you're copying the entire array every now and then, usually it only costs you one operation, and then every now and then it'll cost you order n, right? But on average, it's still order 2, which is really order 1, right? So you can try to do that math if you want, or just trust me on it. So that's how our strategy is going to be. So if we have a stack with the elements A, B, C, and D pushed on, it's going to look like this. So we have some capacity out here, unused space in the array. The bottom of the stack is A, and then we pushed a B, and then a C, and then a D. The top, we're going to have a separate field, is 4, and that's where the next item would go if we were to push it. It's also the number of items on the stack. So by convention, when we're naming things, and by the way, when you're writing code, it's very important to adhere to a naming convention. And it may seem stupid to you because you know what you meant for now, but other people don't. And actually, by adhering to a common naming convention, it takes less thought for less difficult for other people to figure out what you mean. So, or imagine you have to search for the class that implements a stack as an array. What are you going to search for? You're going to first search for the words array stack, not stack array or something else. It helps you if you stick to a good naming convention. And the convention here is going to be that we start with the type of implementation and then we follow with the abstract data type it implements. So this is going to be array stack. Of course, Java didn't consistently do this, but now the API designers do try to stick to that naming convention. So we're going to call ours an array stack, and our solution is going to keep the bottom of the stack at index 0, and it grows. That separate integer top tells you where the top is as well as how many items are in it. And let's look at what that looks like in code. We're in package JSJF, and we're going to need to throw an exception. And I think that there's already an exception that we could have used in Java, but the author defines his own exception types, so he imports them. And I said that there's already a function in Java that will copy your array into a bigger capacity. That method is java.util.arrays.arrayCopy or something like that. So we're importing this package so that we can copy the array. Java docs. And of course, we have our array stack of T, and it implements stack ADT of, and these are the same T. So if you use the same letter, then they have to match, right? So this is the stack ADT of T, right? And then we're going along. We've got our default capacity is 100. So we start off by wasting not 10, as I said, but 100. You can configure that. We have our integer, which is the top, and here we have an array of type T, but it hasn't been instantiated. So we just have a variable that can refer to an array of type T, and we're going to see a nasty wrinkle here on this slide. So let's first look at the default constructor. All it does is invokes another constructor. So in the default constructor, we're invoking the version of this construct. So this constructor down here. This is us. This is our object. We're invoking the constructor that takes one parameter, which is the default capacity. And we need that because we can't put in initializers in Java. So here's the constructor that matters. It constructs the array with a given initial capacity. We set the top to 0 to indicate an empty stack. And this ugly business down here is because our placeholders act like interfaces. and you cannot instantiate them. So you can't say new followed by an interface, right? But we can make new objects, and they'll all be initialized to null. And we can take this array of objects and typecast it to t. So it takes this whole line of code is what it takes to instantiate an array of type t. You can't directly instantiate it with the new operator, but with this thing, a new operator followed by a typecast, you can. And it looks ugly. You've gotten into these corners where the rules of type safety kind of make you have to write code which isn't as clear as you'd like. But this is a stack. This is allocating an array of type t. Okay. And this slide just explains everything I just told you. Right? You create an array of objects and typecast it to an array of t. So again, so the important operations for a stack are going to be push and pop, but we also are going to have this private helper thing that expands the capacity. So let's look at push. So push takes the element you want to push. The first thing that we do is we make sure that there's room for it. So stack.length, this is our internal array, and this is the number of cells available. If the number of items already on there, we've used every spot, then we need to expand the capacity. So after we're done calling expand capacity, then stack will definitely have room, which means that we can now set the top element to refer to the new thing that was inserted, and we can increment top. So we added to the end of the array. Now, how do we expand the capacity? Again, this arrays java.util.arrays.copyOf. It takes one array and it makes a copy of it, but it adds space at the end. So we're doubling. We're going to make an array which is twice as big, and those will all be initialized to null by default. So this kind of made our stack. It didn't do it in place. So this is actually a new array that was a copy of the previous one. And then, of course, the previous one is going to get eaten up by the garbage collector because nothing refers to it anymore. Now, how do we pop? So pop, and here it's saying throws empty collection. I don't know quite how that's working with the interface. But so if it's empty, we're going to throw that exception, empty collection exception. You can look up the details for that, I guess. Now, below here, because we didn't throw the exception, if we reach this line of code, we're going to assume that we're not empty, which means we're decrement the top. But also, we need to return the thing that was in the top, so we're going to hold on to that in a temporary variable. And then, so we don't have a memory leak, we're going to set that top entry to null, so that we're not referencing it from our stack anymore. And finally, we're going to return the result. Okay, so this is a pop. If we didn't set the top thing to null and we figured, oh, it doesn't hurt to just leave it there, then we're going to have memory leaks. It might actually hurt. And then peek. Again, you can't peek at an empty stack. There's nothing at the top. But if it's not empty, then the top element, remember top refers to where the new element would go, not where the last element is. The last element in a stack is actually just before the top. It's at index top minus 1. So in this case, top is at 5, but the last element is at position 4, top minus 1. So, and then of course, after popping E, we decrement top, and then E is set to null, and now the last element was at position 3. So, okay, so now going back, we used an exception there to report that you tried to pop from an empty stack. I would recommend that where possible, you try to see if there's already an exception that you can use. If not, you can define your own. All you have to do is extend an existing exception type, like runtime exception, and then you can implement some of the interfaces for it. So, for example, in package jsjf.exceptions, remember at least there have to be folders that match those names. They've defined their class empty collection exceptions as a runtime exception, and runtime exception in its constructor takes a string, which is what will be displayed if the error actually happens in your code. And what Lewis and Chase have done is they've just constructed a meaningful string provided you give it the name of the collection that generated the exception. Okay. And that concludes this lecture on stacks. I think the next one will again be on stacks, but it will be looking at linked structures like linked lists.